Welcome back to Muddy Math, where we take middle school math concepts that are a little muddy and clear them up. Today's day 19, precision. We'll be slicing cross sections of a square pyramid. So that's a two-dimensional slice of a three-dimensional object to see what kind of stamp we can form from the flat surface that we sliced the 3D object with. We want to know if you can form a 2D cross-section with 5 sides. Is there a pentagonal slice of the square pyramid? Those two understand questions are really asking the same thing using different language. And this whole journey is all about adjusting the way we speak about things and the different perspectives we can take on a single concept. We have a point, which is 0 dimensions, a location in space, a line segment, 1-dimensional, left to right, a square, 2-dimensional, left, right, up, down, from a square pyramid, which is 3-dimensional, left, right, back, forth, up, down. So we're getting 0-dimensional, 2-dimensional, and 1-dimensional slices, cross sections of a square pyramid. You can see here that those cross sections of the square pyramid from opposite vertex to opposite vertex through the apex are forming isosceles triangles. Isosceles triangles are formed by two right triangles. This past week in the 28 Days to Phi journey, we looked at creating paper models of the Pyramid of Giza. Check those videos out if you haven't made yours. A perpendicular cross-section of our paper model through the apex perpendicular to the base also forms an isosceles triangle. There's lots of ways to form isosceles triangles with 2D cross-sections of 3D objects. Can you make a 5-sided slice from a 3D solid that has 5 faces? We're going to be using Play-Doh today to look at 2-dimensional cross-sections of square pyramids. So the point on the pyramid is any of the vertices. So if I were to dip these in paint like so, and those vertices could form points, which is 0 dimensions, and it's just a point is a location in space. And then the line segments are formed on the edges. So if I dipped that edge in paint and dipped it down, it would form a line segment. You can see the triangle faces and the square base. So you can see that the faces and the base are 2-dimensional and they form polygons. So if I were to dip this whole face in paint, I would form a triangle right there. And then the same thing goes for the base. I would form a square stamp. Those are cross sections, but they don't really go inside of the object. To get the trapezoid, I would actually have to slice it. Now, we already saw that if we slice the Pyramid of Giza perpendicular to the base through the apex, then it would form this special isosceles triangle, and these two right triangles form that isosceles triangle, and that's a cross section of the Pyramid of Giza. So if we did that here, okay, I just sliced it. Now it's Play-Doh, so the apex kind of got pulled downward, and you can see how it got pulled downward. It's pretty cool on the Play-Doh. But we can sort of patch that back up, and you see that the face of the pyramid has a taller height than the cross section through the apex perpendicular to the base than that isosceles triangle. So those are two different isosceles triangles that we can form. How do we form the trapezoid? Something a lot of my students try to do when they do this activity in the classroom is use multiple slices, and that's all well and good, but traditionally when you think about cross sections of an object, it's with one slice. So we'll see how we can form a trapezoid with one slice. If I go straight through the apex, I'll get an isosceles triangle. So if I come forward or go backwards from the apex, then I ignore the pointiness of the apex and I utilize the flatness of a little bit off of the apex. So then when I pull it away, you'll see that it's a nice trapezoid. So we can get trapezoids. Okay, what if we twist this slicer a little bit. When we do that, we get a quadrilateral that is not a trapezoid. So a trapezoid requires that the two bases are parallel, and in this case, these two lines are not parallel, so it's just a simple quadrilateral. Well, it doesn't have to be simple, but it's a quadrilateral. Now, we've only formed geometric objects that have up to 4 sides so far. We've not been able to form a circle from a cross-section of a pyramid. But if we look at the cube, we'll be able to see how to form a pentagon with a cross-section of a cube. How many faces does a cube have? Think about a dice. How many sides to a dice? It's called a face, not a side, because a side would be a two-dimensional reference to like an edge. There's 6, okay? So there's 6 sides to a cube, and the way that we can get a pentagon is by making sure that our slice goes through 5 of the 6 faces. So we have to angle it and plan ahead so that we can get 5 of the 6 faces. So if I get this one, I can score the Play-Doh. So that was the vertex of the square, and then the way we sliced it, we have a really cool funky pentagon here, a side here, 1, 2, 3, 4, 5. So it's a little wobbly because I'm using Play-Doh, but a pentagon formed from a cube works. See if you can intersect all 5 faces, and including the base of the square pyramid, to form a pentagonal cross section. Day 19, thank you for tuning in. I'm so proud of you. Thank you for carving out this time for yourself each and every day to look at the natural world around us with a mathematical perspective. I really hope you have someone to collaborate with on this journey. If not, leave me a comment, go to muddymath.com, or email me at muddymath@gmail.com, and I'm happy to be that collaborator with you. Find math around you in the simple things that you may never have really expected it to be before. My connection to all these cross sections is to see what the cross section of a pine cone will look like. I've tried to cut it already and it did not work. It was too strong. So I'm gonna see if I can figure out a way to get a cross section of a pine cone, or a bunch of cross sections of a pine cone, and maybe apply that to my drawing. My painting is sort of the top-down perspective, the bird's eye perspective of the pine cone. I wonder what a cross-section of the pine cone would be like. Sam signing off from Muddy Math. Thanks for tuning in. I'll see you tomorrow for day 20.